today, so let me get into student planning. Oops. All right, Mr. Amore, are you here? Not yet. Mr. Burns, you're here. Mr. Fisher. Here, Mr. Runge, not here. You're here. Mr. Trailer, you finally are back. Yay. And let's see what dirtbag's about to walk through the door. Mr. Amore. And hopefully... No? Okay. I'll have to... There he is. Yeah, probably a good thing. Yeah, so... All right, well, let's get to it. So those of you who just came in, grab one of the sheets off of the desk there. And hopefully Mr. Kung will see fit to join us shortly. So, and my audio keeps cutting out, which is getting really annoying. All right, Mr. Kung, you're here. Okay, good, everybody's here. Okay, so we're numerically, and this is getting really annoying. I don't know why it keeps doing this. Well, whatever. Okay, so we're going to sort of do this to motivate the idea. So what I'm going to do is I'm going to use a program here called Mathematica. And once I get it open, and then I'm going to blow it up a little bit and switch over to full screen so those of you at home. Wake up, Sonny. Okay, so is this kind of weird exponential function? So it's so I'm going to define a function. What's wrong? What's wrong? Oh, that thing, not the. Okay, well, I thought I switched to source. 2. Okay, there we go. So, yeah, there's some sort of bug in OBS where if you tell it to screen the full to squared. Okay, so I just defined the function, no big deal. And then let's just kind of plot it over the range of, say, -2 to 2. Well, let me do -3 to 3. Just to kind of get an idea for what's going on there. So, all right, kind of a weird looking function. Nothing, particularly exciting. Except what's going on over here at 2? Sure looks like the function is like really flattened out at 0 there, okay? So what we want to kind of do is investigate 2. Okay, I'm getting ready to like fly to Cupertino and punch Tim Cook in the face. Because I do not know why my AirPods keep disconnecting and reconnecting. It's getting very annoying. Okay, says they're connected now. All right, so let me redo this, but instead of negative 3 to 3, let's go 2 to 3 so that we're, oops, sorry, not 2, 1 to 3, so that we're kind of centered in on what's going on. All right, so if we were to look at this graph, first off, let's be clear, I cannot plug 2 into the function, right? So f of 2 is big time undefined, right? Because what would happen if I did try to plug in 2? I'd get 2 to the undefined, and the reason I'd get that is because, well, x minus 2 that's there gets squared, but 2 minus 2 is 0, and then I'm dividing by that, so that's verboten. We got a big problem, okay? So the function's not defined at 2. So the fact that the graph looks as if it is defined at 2 is more of an artificial, like, it's a computer problem. So this is like, you guys remember in high school, did your teachers ever say, like, your calculator will lie to you? No? They never said that? Okay, well, my high school teachers always did. Okay, so that's sort of the problem. But what can we do? Well, let's kind of try and zoom in on the problem, right? And so let's do that. Okay, now this looks a little funky because look at the range of the y values here, right? Really ridiculously small. Okay, so so what's our guess for what's going on here at 2? Or close to 2, rather, let's be clear. Yeah. Yeah, just a little hole. Like if we were to draw this by hand, we'd put a hole there. Okay. All right. Now, the other thing we can do is, so notice on the sheet there, we've got a little table that we can fill in, right? And 5. Okay. And then similarly, we want to do this for all the other values. Okay. So 2.5, all right, 0.0625, great. That uh, there's sort of a limit to, and those of you who take, say, CS 101 or something, this is something vision. It's the floating point stuff. And this number is smaller than that smallest little increment. Okay, so it's basically truncated it off. Okay. All right, so what, let's go over to the iPad for a minute. What we want to ask ourselves is what should we make of this limit? Okay, so we should be on the, oh, got it. Okay, so what do I mean when I say, when I write lim x approaches 2 or something? I'm asking, what, if I plug in numbers that are closer and closer to 2, what does the function's value approach, if anything? Okay, now that's distinct from asking the question, what is f of 2? What is f of 2? Right, undefined. We already dispensed with that. So the value of the limit and the value of the function, if any, could be completely different things. Okay, now based on our number crunching, okay, so this isn't proof, but this is sort of conjecture. What do we think that this limit should be? 2? 0. Okay, so now here's the difference, right? Why? So where did the 2 come from? Like,
every time you get close to 0,
well, right, okay, so the x values are getting close to 2. And what we're asking is, as the x values get close to 2, what are the y values getting close to? Okay, and that's 0, right? So x versus y is, x is approaching something, in this case 2, y 2 because that's sort of the point where things look like they're going to be weird. And then what do the y values approach, or seem to approach? They seem to approach 0. Okay, so we would guess this based on our number crunching. Does that seem reasonable? Okay, now, let me be clear. Doing this number table thing on the sheet, which, by the way, for those of you who are online, you can grab the sheet out of the file section on Canvas. It's section 1.1 sheet. Okay, so, but the value of the function and the value of the limit could be two completely different things, okay? Now, so what we are kind of trying to do today is build our intuition as to what limits ought to be, and then Wednesday and with subsequent stuff we'll kind of say, all right, enough number crunching, enough graphs, how do we do this algebraically and not just wave our hands in the air at a picture. Okay? But today is pictures and tables. Okay, so let's look down at the little graph on the bottom corner there, and I'll just kind of make a crude sketch of it. So it was sort of something like this, and then there was a hole here and a hole, say here, and a dot there. Okay, and then the axes, 1 was here, 3.5 was here, and so stuff's in the middle. Okay, and so what we want to ask ourselves is what, if anything, is this? Okay, so looking at the graph, what are the y values approaching as we get close to 1, x equals 1? What does it look like? Y equals 1? Does it seem reasonable? No? Okay, so we would say that this limit is 1. Okay, now, two other kind of interesting points. What about if we were looking at 2? Is anything weird happening on the graph at 2? We don't have any holes, there's no discontinuities, no asymptotes, anything like that. So in this particular case, what is this limit? What's it look like that? F of 2, which is numerically about what? Negative 1.5? Okay. Okay, so here, it just so happens that the limit's value is exactly the value of the function. That doesn't always happen, but it does happen when things are going nice, okay? What's maybe a better word for nice when it comes to the graph? Like, let's get like a $500 SAT word. Continuous. Ding, ding, ding. Okay, so what was the definition of continuity in high school?
being defined by like interacting on one
Okay, that's maybe better. You went to a good high school. What about drawing a picture, drawing a graph without picking up your pencil? You guys remember that definition? No? Yeah. Okay. Well, yeah. So when it happens that the limit and the value of the function are the same thing, that actually is going to be what defines continuity. We'll talk about a lot more about that later. Yeah. So sometimes it does happen that way, but not always. Okay. So similarly on this one, what's going on at x equals 3? Anything weird? Nope, looks good. But 3.5, what's going on there? Yeah, we've got a hole. So 3.5 is the tricky one. Okay. What is the value of f of 3.5? What on the graph am I looking at to make that determination? It's, yeah, 2. Okay, how did you know that based on the graph? That's where the dot is, the solid thing, okay? So, are we clear on that? Okay? So the value of the function, f of 3.5, is 2. What's the value of the limit? -1. Okay, what told you that? Right, so what's the y value of the whole? That number, right? Okay, not the dot, but the whole. Okay, so you guys see the distinction here? Don't care about the y value, I mean, do sometimes, but what the y values are approaching is different than necessarily with values. And this one is sort of artificially constructed to make that clear. Okay. All right, so does that seem reasonable? Okay, so from a graph or from a numerical table, we can get a sense for what we think the limit might be. And then we'll start to do some algebra and to be rigorous with this because, well, it's not like you always have a graph or a computer at your disposal anyway, which I guess is a little bit silly. Okay, so flip the page. The next thing is kind of, see how to put this, technical. So there's lots of things that we want to be able to deal with. So for example, let's say that we have two limits of one function. Oh, and let me use the same letters here. Okay, so we got two functions, f and g, and we're approaching some x value. Let's just use c, whatever. And I'm saying, suppose that these two functions have those two things as limits. Okay, one of them is L, the other one is K, whatever those numbers are. Okay, so the question is, what would happen if I took the two functions and I added them together and then asked, what's the limit of this thing? Well, what do you think? Okay, so what does it mean to add two functions? Like if you were to draw a graph of them or something. You're kind of shrugging over there. You never understood limits or graphs? Okay, well forget limits. I give you two graphs, f and g, and I say, I want you to graph f plus g. What are you going to do? Owen? Feed it into you. Huh? Okay, let's say that I give you two functions written in Python, okay, and I ask you to define the function that's the sum of the two things. Yeah, okay. So, you know, if I have a function f and a function g, and I ask you to compute f of 3 plus g of 3, what do? You evaluate f of 3, you get something. You evaluate g of 3, you get something else, and then you add those two things together. Okay? So if that's the case, right, that's how we add functions, what do you think is going to happen to their limits if we add them? What do you think? Yeah, just the two limits added together. Okay, so this is the first of a bunch of sort of algebraic rules about how limits work, is that the limit of a sum is the sum of the limits. Okay, and if the first limit was L and the second limit was K, then what should this answer come out to be? L plus K, whatever that is. Okay, does that kind of make sense? Yeah? All right, now, was there anything special about addition here? Could we have done subtraction instead? Well, what happens then? Instead of being plus, it's minus. Okay? What about multiplication? What do you think happens there? Okay, so if I had the function f of x times g of x, what is the limit of that going to be? LK, right? It's the product of the two limits. Okay, so where's the one case where we have to be a little worried? If we've done addition, subtraction, multiplication, and therefore what comes next? Yeah, we've got a little bit of a problem with division. Okay, what's the potential problem with division? Yeah, if the thing that's in the denominator is 0, we're hosed. Okay, now what about if the thing in the numerator is equal to 0? Is that, like, is it okay to divide something, or divide 0 by a number? Yeah, that's fine, unless you're dividing by 0. Okay, so 0 in the numerator by itself, no problem. It's 0 in the denominator where we're SOL, okay? So, all right, so let's just write that down. So the limit as x approaches c of f of x divided by g of x is L over k, provided that k is not 0. Okay, so it can't have a 0 in the bottom. Now, one thing we will talk about, and this is a little weird, is what happens if both L and k are 0? Okay, so we have 0 divided by 0. What is that? Huh? It's kind of worse than that. Like asymptote type stuff can happen there. In fact, this is sort of a freaky thing. Pick a number. I can come up with an example where 0 over 0 should equal 7. Pick another number. Same thing, right? So the moral of the story is if you get 0 over 0, it's basically the mathematical equivalent of saying WTF. Okay, we have no idea. We have to do extra work to figure it out. We'll need to talk about that until your eyes bleed. Okay, so the other rules here should look relatively familiar, okay? In the sense that things work the way you would want them to, right? Limit of a sum is the sum of the limits. Limit of a difference is the difference of the limits, etc. Okay? And so what this means is that if we have some really nasty looking function, we can break it up and say, okay, what's going on for this little part, what's going on for that little part, and then just put all the answers together. Okay, so it allows us to kind of simplify what we're working. Okay, so now, another thing is, for example, let's just write these two basic ones down. What's the limit of a constant? Would it make sense that it should be that constant itself? Okay, that's kind of like the definition of the word constant. What else would it be? Okay. Okay. Similarly, what would happen if I took the limit of x as x approaches c? You're going to be shocked, because what do you get? C, right? If x is approaching c, what is x approaching? Oh, I don't know. C, right? I mean, it's almost so obvious it's stupid to even say it, but yeah, okay. So if you've got, well, all right, so if x is easy, what about like x squared or x cubed or something like that? What do you think we could do? So like, what do you think the limit of x squared is as x goes to c? C squared. Yeah, okay, so polynomials are going to be really easy to deal with, right? You just plug stuff in. Okay. But as we'll see, other functions aren't so much. Okay, so these limit laws are kind of, they're abstract in the sense that the statement on the second page there, right, is very general in terms of L's and K's and whatever, right? And we stuffy mathematicians like to be abstract because you know, we can write something down that's true no matter what these numbers are, rather than having to write down like 10 million examples of it. Okay, but let's do some examples that are a bit more practical. Okay, so flip over to the third page there. Okay, so here we've got two functions, f and g, and we have, for each function, 3 pieces of information, okay? What the limit is as x approaches 9, what the limit is as x approaches 6, and what is the value of the function, either f of 9 or g of 6, okay? And these numbers are just kind of picked at random here. So, okay, so given that information, what's the limit as x approaches 9 of f of x plus g of x? What two things do we need to know to answer that question? Right, okay, so we need to know two pieces of information. What's going on as x approaches 9 of the function f, and also the function g. All right, so what's going on for the function f as x approaches 9? What's that limit? 6, okay? What's the limit as x approaches 9 of g? 3, okay, so what should we get there for part A? Okay, and we're getting that because it's 6 plus 3. Does that make sense? No? Of course, my email is already blowing up this morning. It's not even 8:30 and okay, good. Now, so let's continue with this. What about part B? Okay, so we got a little 2 wrinkles in part B. What's the first thing that we might need to worry about? Yeah. Yeah, we got to do the f of x times 3 because there's that constant sitting in front. Okay, so there's one problem or thing to deal with. What's the other problem, potentially? Yeah, we've got a division, okay? And so we're going to have a problem if the bottom thing is 0. Okay. Now, fortunately, it isn't, but it could have been. So what's the limit as x goes to 9 of f? What did we say there? It was 6, okay? What's the limit as x goes to 9 of g? 3, okay? So what should this one come out to be? 3 times 6 divided by 3. Okay, now why is it that? And let me just write down what and it was what, 3f of x over g of x. Okay, where's the 3 in the numerator coming from? The statement of the problem, right? So it just so happened that there was a 3 right here that was given. Okay, so this 3 is just that 3. Right? Because what did we say the limit of the constant should be? Just itself, right? It would be there. All right, what's the limit of f as x approaches 9? What did we say that was? 6. Okay, that was given. And then what's the limit as x approaches 9 of g? 3. Right? And then in this case, the 3's happen to cancel, and so we just get 6. Okay. Oui ou non? Non? Oui? Vous avez quelques problèmes? Vous parlez français? Vous êtes un sérieux pour le classe, n'est-ce pas? Parce que vous parlez français. Yeah, the rest of you, it's too bad I'm not actually like super fluent in French. I think it'd be kind of fun to just walk in the first day and just speak nothing but French for the whole day and just I've heard a story though. You guys know Professor Topol? No? Okay. Well, anyway, he's obviously a native Spanish speaker. Heard a story that many, many years ago, he's got a calculus class like you guys, and everybody's just kind of nodding off. Nobody's paying attention. And so he just switched into Spanish to see how long it would take everybody to notice, to say something. Maybe one of these days I could do that French, but whatever. All right, so let's going to continue this thing. So look at C there. C looks a little bit more complicated. So what really are we going to do there? So x is approaching 9, and the thing we're taking the limit of is f minus 2g all over g. Okay, so how are we going to build up the answer here? All right, so let me just write that down. So we got limit x approaches 9 of this thing. Okay, first off, what's the potential problem? Right, that the denominator could be 0. Is it, in this case? No. Okay, so we're cool. All right, so I'm going to be a little pedantic here, and I'm going to go ahead and write this. Okay, so what did I just do there? I just wrote out what the limit laws say, right? What's the limit of the quotient? The quotient of the limits, so as long as the bottom is 0. You really make sure that that wasn't a problem. Okay, and so then in what's the limit of the numerator? Well, the numerator is two functions added, or in this case subtracted, right? So what's the limit of the difference? The difference of the limits, and then that 2 that was hanging out there, that constant, what's the limit of the constant? Just itself. Okay, so I can just sort of use it. Okay, so symbolically that's what we're computing here. Right? The limit laws say that we can do that, and then we just need to fill in all the different pieces of information. So what are the 2 limits that we need? What's the limit of f? We said it was 6. What was the limit of g? 3. Okay, so in this case we get what? 6 minus 2 times 3 all over 3, which happens to be 0. Because the numerator is 0. And again, if the top part's 0 and the bottom part's anything but 0, we're okay. No worries. Okay, good? All right, so let's look look down at D. Okay? What's the potential problem, again, that we might have with D? The denominator could be 0. Okay? Is it? Yeah, okay, because what's x approaching this time? 6, not 9. Okay? So as x goes to 6, what is g of x? What's that number? 3. Okay, and then what's the problem in the denominator? We've got 3 minus that quantity. Okay, and last time I checked, 3 minus 3 was 0. Okay, well, womp womp. Okay, so, could we answer this question? In the sense that, can we write down a number that's the answer? Okay, we can't. So what should we write down instead? Undefined, indeterminate, does not exist, infinity. Okay, what's the correct lingo here? Okay, and in this case, we would say it is does not exist. Okay. So what's the difference between does not exist and being undefined? This is kind of a philosophical thing. Okay, the difference is this. Oh yeah, go ahead. Okay, yeah, undefined, like, well, like take for example, what's an example of a situation where you have an undefined thing for a function? Okay, 6 over 0. Or I'll take another one. Let's do something like the square root of -1. Right? Is that undefined? Well, depends on who you ask. In this class, what is it? Well, it'd be I. Right? I squared is -1 then. Right? So, yeah. So maybe that'd be a situation where it's sort of undefined in one context, but not in another. Okay, now. So the difference, though, is definedness is about functions. Okay? Are we talking about functions here? Sort of. But what really are we talking about? Not the function's values, but rather the limit of those values. Okay, that's a different kind of object. Right? Okay, so we use different lingo with limits when they break. Okay? In this case, it does not exist. There is no number that I can write that's equal to this limit. Now, in some cases, and we'll get to this in a bit, we can be a little bit more descriptive as to how it doesn't exist. Like maybe it blows up to infinity, or maybe it does some other weird thing. Okay? But for right now, A, we don't have any more information about these functions, so we can't say much. And B, well, we got a problem. We got a 0 in the denominator. So, don't know. Okay, so does that kind of make sense? Okay. So, why don't we do the following? Well, actually, okay, let's look at E, F, and G. Okay? So, what kind of operation is going on with the two functions in those examples? It's not addition, subtraction, multiplication, and division. It's something else. What is that called? What are we doing there? Yeah. Yeah, it's a composition of functions. Okay? We're basically plugging one function in as the input of the other function. Okay? Is that, you guys remember the word composition? Okay, so what does it mean to do? It means to plug one function into another one. Okay, and actually, you guys probably remember this other notation from high school, right? F with a little circle G, right? And what did this mean? Oops. This meant to do f of g of x. Okay, now here's the annoying thing about composition. If you do this computation here, let's say I give you a number, which function do you compute first? maybe feels a little backwards, but I don't know. Okay. All right, so the question then is, how do limits play with composition? Well, that can be a little tricky. So let's just take the first one. It happened to be, actually, since I'm doing f of g of x, let's look at part f here. Okay, so here we have the limit as x goes to 6 of f of g of x. Okay, so what I'm going to do is I'm going to say, all right, what's going on g of x? If x is approaching 6, then I need to know what the inside function is doing when I get kind of close to 6. What is limit as x goes to 6 of g? What was that given to be? It was given to be 9. Okay? So what do you guys think this is going to be? I'm going to guess that it's f of 9. Okay? Because the inside thing is, yeah, did I mess something up? Oh, sorry. The peanut gallery has led me astray. 3. Okay. Okay, so we get that. Now, what is f of 3? Do we know? We don't know. Okay, so in this case, since we don't know what f of 3 is, we can't go any further. Okay? Now, I just kind of did something, which is I slipped, effectively I just slipped the limit inside the function f. Okay? And whether or not I'm allowed to do that, we kind of need to know a little bit more about f to justify whether that's okay. Okay? But in this case, we're kind of boned anyway because we don't know what f of 3 is. Okay? Now, let's contrast this. What about the one that was right above it? There, the function composition happened in the other order, g of f. Okay, so what's that one? Limit as x goes to 9 of g of f of x. Okay, first off, before we even worry about the limit, is f of g of x the same as g of f of x? In general, big time not, right? You compose them in the other order, and you could get a completely different thing. Now, sometimes it works out as the same, but that's sort of really lucky when that happens. Most of the time it doesn't. Okay, we do not. Okay, right here. So, like what we did last time, what should we be looking at here? Do we know what the limit of f is as x approaches 9? Yeah, we know that, what was it, 6? It's this. Okay, so what are we going to guess that our answer should be? G of 6. Does that seem reasonable? What is G of 6? Is that a given piece of information? Is it on the sheet there? G of 6 is 9. Okay, so what do we think this limit is? Oh, careful. The whole thing. Yeah. So the inside part is 6. Right, but then G of that. And G of 6 was given to 9. Okay. So this would work. The one that we did just before it did not work because we just didn't have that information. Okay. So composition, I guess, is the one that could be tricky. And then just to kind of keep things nice and spicy, look down at the very next one. What do we have going on there? Yeah, triple composition, right? So it's g of f of f. Okay, so what do we need to look at? We need to look at the innermost thing first. What's f of x do as x approaches 6? It was 9. Okay, that was given. Do we know what f of 9 is? It's 6. And do we know what g of 6 is? Okay, so what is this going to work out to? 9. Okay, we happen to know all the requisite pieces of information. That was nice. Okay, but you see, what did we do? We worked our way from the inside out. Right? Start with the inside thing, figure out what that limit is, and then there's no more limits. It's just plugging numbers in. Okay, so does that kind of make sense? Okay, and then the very one there at the bottom, what does F2 and G2 mean? Like to the 2 there, what does that mean to do?
Means that it's supposed to be squared.
Yeah, they're both squared, exactly. Okay, so writing F2 like this. This is lazy mathematician writing for that. Okay. Warning, however. What does this mean? Does this mean 1 over f? It means the inverse. Okay, so that's the one exception, and this is really annoying. Okay, so if I say the word inverse, what do I mean? There are at least like 4 or 5 different senses of the word inverse that we use in math, and we use all of them simultaneously. Right? If 2 numbers add to give 0, they're inverses of one another in an additive sense. If 2 numbers multiply to give 1, they're inverses in a multiplicative sense. If 2 functions compose to give x, they're inverses in a functional sense. Okay? Does that drive you crazy that we use the same word for lots of things? Sorry. Yeah, it's really unfortunate. Okay, so that's the one exception. If the exponent looking thing is a -1, then it means function inverse. So, for example, where do you guys run into this? This is a good one. Okay, I will never ever write that again. If I mean the inverse, this is why I like to use arc sign instead of, like for trig functions is where you run into this a lot. Okay. It's an unfortunate piece of notation. It's, if I had a time machine, there's a few things about math I would change. This would be one of them. I'd also take a sports almanac with me. And yeah, there we go. Okay, good. Somebody got the reference. From Back to the Future. Yeah, okay, just checking. Yeah, take a sports almanac and then also hit a few mathematicians and say, no, don't write it that way. Just trust me. So, yeah, anyway. Okay, so that's all that 2 means is just square it. It's shorthand, okay? Okay, so does this kind of make sense, right? This isn't rocket science. And we'll talk a little bit more about how to be more precise with limits, and how to, doing the number crunching or the graphical thing is good to build our intuition, but it's only the beginning, not the end of the story. So, okay. All right, well, I will see you guys on Wednesday.